Today's problem of the day, smaller on left. Given an array ARR of n positive integers, the task is to find the greatest element on the left of every element in the array which is strictly smaller than itself. If this element does not exist for an index, print -1. So we are given an array ARR of n positive integers, and our task is to find the greatest element. That is, if we are standing at here, we need to find the greatest element on the left which is strictly smaller than this 3. So if we look at this, if we look to the left of 2, 2 is the largest element which is smaller than 3. So in such questions, the first thing that generally comes to our mind is stack, because we have seen some problems finding smaller elements to the left, the next smaller element, the next greater element. But here there is a small tweak, because here we are not asked to find the next smaller element or next greater element. Here we are asked to find the greatest element on the left which is smaller than the current number. So, suppose if we are at 5, we need to find the greatest element. Okay, there are so many numbers that are smaller than 5 here. There is 4, 3, 2, so many numbers, and from those lists we need to get the smaller number. We need to get the larger number. So here if we consider 2, 3 and 4, the larger number is 4. So for here the stack will not be an option, because if we consider, like, if we here in stack, like, we will be popping the value out. Whenever we say any number just greater than or smaller than the current number, we are just popping it out. We are making use of a monotonic way. But here it will not work, because we need to find the strictly smaller number, the greatest smaller number. So let's have this example. Let's walk through it. 2, 3, 4, 5 and 1. So we are at 2. What is the smallest number less than 2? To the left. Which is the greatest smallest number? Okay, greatest number smaller than 2. To the left there is no such elements, so we have -1. -1 indicates like we are having no values which is smaller than 2 and which is the greatest. Okay, now we have 3. What is the number to the left which is smaller than this 3 and that is the greatest among that set? Here we are only having one value, 2, and this 2 is less than 3, so we have a value. So to this index, like, we will be having 2. Okay, now we are at 4. We look for the left. To the left we have 3 and we have 2. Both are smaller than 4, but we need the largest among them. 3 is the largest among them, so this will give us 3. Now we are at 5. So in 5, this is 4. Okay, this is 3. Okay, this is 2. So all these values are smaller than 5, but we need the greatest among them, and the greatest among them is 4, so we have 4 here. Now 1. Are there any element to the left of 1 which is less than 1? No, we can't see any number, so this will return 1. This is the first test case. Now let's go for the second one. 1, 2, 3. So same way, it's the same condition, 1, 2, 3. So one thing that we can observe is, for the very first number the value is always -1, because there is no number to the left. Now 2. To the left, are there any number that is smaller than 2? Yes, there is one number, that's 1. There is only one number, so surely that is the one we are looking for. Now 3. Are there any number to the left of 3 that is smaller than 3? Yes, we have 2 and we have 1. Okay, and among them, which is the greatest? 2 is the greatest. So this is the one. So here what we can do means, we can make use of there is a concept like a tree set. So tree set in Java, like tree set means if we add values to the tree set, like it will be arranged in a sorted way. It will be adjusting themselves and it will be in a sorted order. So if we add, like first of all, like our suppose consider this is our tree set. So first of all, it's empty. So there is a method that we can use inside. It is set dot lower of number. Set dot lower of any number. I'm just considering now. So what this means we are checking inside this method. Generally check inside the set, are there any lower number, okay, which is lower than the num, and that is greatest. It's very much identical to the problem statement. We need the smallest number, which is the greatest. So the same thing, it's also given in the geeks for geeks. So here is the tree set, is the return the greatest element, which is strictly less than the given element. So that's identical to our problem statement. So we can just make use of this method. Okay, so at first, if we consider 1 2 3, at first we are checking whether there are any number that is less than 1. No, because there is nothing inside the set initially. So the value, so here the thing what the value we will be getting will be null. So if the value is null, we can set that particular index as -1. Okay, now we will be adding, sorry, this is a set, sorry. Now so let's have a result here. Suppose this is the result, we have -1 here. Now we will be adding this one to the set. Okay, we added this one. Now 2, same way we just check whether set dot lower of 2. So set dot lower of 2, we are having value 1. So this will be having 1 and it is not equal to null. So that index will be appended or added the value 1. Now we add this 2 here. Okay. So now we have 3. So set dot lower of 3, it will be return the greatest number, which is strictly less than 3. Yes, we have 2 and it's not equal to null, and we got that answer. So that's what we are looking here. So if our so the base condition, if our n is equal to 1, return -1. So here, like normally if we didn't apply any comparator or anything, okay, custom comparator, like it will be in the increasing order. The tree set will be arranged themselves, like they will be balanced themselves in a in an increasing order. Otherwise, if we use some kind of a custom comparator, we can arrange it or sort it as per our need. So if our we are only having one element, will there be any value to the left which is smaller than that number? No. So we need to return new int of -1. Okay, now let's have our result array, and this result array will be same as that of our array, because for each of the element we are finding the smaller element, greatest smaller element. Okay, now we have the result array. Let's fill it fully with -1, so that we don't want to take extra step in order to fill the remaining spaces with -1. Initially all the result will be -1. Okay, now as told, we also need a tree set. So tree set of integer, we can have this sorted set values is equal to new tree set. As the name suggests, like it will be arranged in kind of a tree, like a structure, self-balancing tree, we can say like that. Now for each of the value, for int I is equal to 0, I less than I plus plus. As I told, like first of all we will be looking this one. Okay, so it will be giving a integer wrapper. Okay, wrapper object. If the value, smaller value equal to, okay, sorted. The method is sorted set values dot lower of nums of I, means the greatest element which is strictly smaller than nums of I. So initially at the very beginning stage, if we are at this index, there will be no such values. So our smaller value will be null. So we need to just check if our smaller value is not equal to null. That means we got a smaller value which is greater than the current element. Sorry, we got a smaller value which is the greatest. So result of I will be equal to what do you say, array of I, sorry, it's smaller value. Now we need to add the current, the nums of I into the set. Sorted set values dot add of nums of I. Now just return the result at the end. So here, as I told, like when we add values into the hash set, like it will be sorted internally, like there will be a sorting happening. So the time complexity will be n log n, and we are also making use of an extra space here, and a big of n, like we are adding all the values into the hash set, so we are having a space. So the time complexity will be n log n, as there is a sorting happening in the hash set or the tree set, and the space complexity will be a big of n for the result plus a big of n where we are adding all the elements to the set. So big of n plus big of n will be the space complexity. Okay, so let's compile. I'm getting a smaller, okay, it's, sorry, my mistake, array of I. Okay, now it will be fine. Okay, minus 1, 2, 3, 4, minus 1. Okay, now let's submit it. So the time complexity, once more, time complexity will be n log n, as there is a sorting happening inside the hash set. Okay, and then space complexity will be a big of n for the result. If we are considering it towards the space complexity, then we are having a big of n space complexity plus big of n for this tree set. So that's the solution for the problem of today's problem of the day. Yeah.